Hello. We are going to see some examples of functions that I think are important for the early courses of mathematics at the Polytechnic University. We are going to start with the function x squared. It is very simple to represent this function. If we give values to x, we will obtain the values of the y. In this case, they are given by x squared. Therefore, if, for example, we take x equal to 2 and substitute it in this function, the function would provide me 2 squared, which is 4, and as you can see, more or less, would be this point here. If we take the value of x equal to 4 and substitute it in the function, we would have the value of 4 squared, which is 16. And therefore, you could see more or less that this point would be here. What happens when we take negative x values? It is very simple. Negative by negative is equal to positive, and therefore, it is also represented on the positive part of the y-axis. For example, if we take the value of x equal to minus 2 squared would be 4 positive, and therefore, we would have this point here. If we take the value of x equal to minus 4 and substitute it in the function, we would have minus 4 squared, which would be 16 positive. Therefore, it would be this point here. This graphic representation has its name, and that is parabol. And it will appear many times. Let's go with another function, which is also very well known. It is the function x cubed. And its graphic representation, you have it here. Look at the shape of this function. Both branches cannot be upwards because of negative values of x. This function also takes negative values. Look that it is raised to the cube. For example, if we take x equal to minus 2, minus 2 cubed would be minus 2 by minus 2 by minus 2, which would be minus 8 down here. And the same would happen with the positive 2, but with a positive sign. 2 cubed would be 2 by 2 by 2, which would be 8, which would be up here. As you can see, the scale in the y-axis is not the same as in the parabol. There it was from 0 to 15, and in this one, for the same range of x, it goes from 0 to 60, practically. That means that the function x to the cube grows much faster than the function x to the square. This graphic representation also appears in many exams. So please, memorize it if you can. Another of the important functions is the square root of x. In this case, we cannot represent it for the negative values of x. We can only represent it for the positive values. Why? Because the square root of a negative number does not exist. As you can see here, the shape of this function is a function that grows from 0 to infinity, and it often serves us to intersect it, for example, with the function x squared. And to ask you, which is the enclosed area between these two functions? Let's take a look at another function that I also think is important. In this case, for example, the sine function will appear millions of times. I have represented it for values between 0 and 2 pi. Notice that it is the curve that would repeat itself infinitely. For example, I am going to change the 2 and I will put an 8, and you can see how the function is repeated many more times. I follow the same pattern. It's a function that we call 2 pi periodic because it has the same graph every 2 pi periods. Instead of the 8, I am going to put the 2 because I want you to compare it with the cosine function that comes next. By the way, you could represent it by giving values to the x and knowing a little what is the value of the sine in those values. For example, in 0, everyone should know that the sine of 0 is 0, so we obtain this point. For the value of half pi, which would be 90 degrees, which would be more or less around here, the sine of half pi is 1. That is why the graph reaches its maximum here. For the sine of pi, everyone should know that the sine of pi is 0, and the sine of 3 pi half is minus 1. Here you have the graph of the sine function. Now we're going to see what the graph of the cosine function looks like, and then we compare it. The cosine is practically the same as the one we have above. Now you will see that it is a little displaced. As you can see, it can also be obtained based on giving values to the x. And of course, you have to know what is the value of the cosine in those points that you choose. In this case, for example, if we take the x equal to 0, we have that the cosine of 0 is equal to 1, so the function begins here. The sine of half pi, which would be around here, also in this case is 0, and the cosine of pi is minus 1. And this would be the cosine of 3 pi half and the cosine of 2 pi. How do these graphs relate? Take a look at the following graph. In this one, I have represented the sine and the cosine between 0 and 2 pi, both at the same time. As you should recognize, this one here is blue, it is the sine, and this one here is the cosine. As you can see, it's essentially the same wave, but shifted. We are going to increase the range so that you can see what happens. We are going to put, for example, from 0 to 10 pi. In this case, as you can see, it is a wave, the blue is the sine, the red is the cosine, and it is practically the same wave, but shifted. Let's see one more example, a bit unusual one. For example, the tangent. The tangent, as you will remember, is sine divided by cosine, and its graphical representation is a little stranger. Let's analyze it a little. The tangent of 0, when the x is worth 0, the tangent of 0 is 0. So at this point, there is no problem. The tangent of 1/4 of pi is equal to 1, which would be more or less around here. Why is there a vertical line here? Let's try to explain it. The tangent in, for example, half pi is not defined. We know the function grows significantly, approaching infinity, but it will never reach this point. The function does not pass through here. Here there is only one vertical asymptote that the program has drawn to indicate that there is no function there. And then it comes back from negative infinity. It goes up until it reaches a value of 0. At what angle? Let's make it an exercise. Then it does the same thing again. It keeps growing until it encounters the next point where it's not defined. For example, 3/2 pi. In that point, it is not defined either. It is much more complicated to represent the tangent than the sine or cosine as we have seen, but it is also important that you know a little about its representation because it also appears quite a lot. Let's go for other functions. This one is a bit more peculiar. In a previous chapter, we have seen how the hyperbolic sign of a function is defined. But I wanted to represent it at this moment because its graph should remind us of another function that we have explained previously. Let's go a bit higher. This graph bears a significant resemblance to that of x cubed. Are they exactly the same? Not at all. They are not the same. Let's represent them together and see. Okay, here you have the hyperbolic sign. If we represent them together, you could see how is the difference between x cubed and hyperbolic sign. In this case, the blue represents x cubed and the red is the hyperbolic sign. As you can see, the hyperbolic sign from a certain value grows much faster than the function x cubed. Why do I represent these two functions together? Because many times it is difficult to remember which is the hyperbolic sign graph. But I hope that if you associate a little the idea that it resembles x cubed, you can represent it at any time. Let's go now with the other hyperbolic function that I think could also help you with the representation. Hyperbolic cosine of x. It also resembles a lot a function that we have already seen previously, and it is the parabola. In this case, notice that here it does not start at 0. It does not go through the 0.0. It's a bit shifted upward along the y-axis. What is the difference, apart from this obvious one, between x cubed and the hyperbolic cosine? Take note, in this case, the difference that it is shifted upwards is not appreciable because the hyperbolic cosine function grows very rapidly. In this case, the blue is x squared, and this red is the hyperbolic sign. Notice that, for example, the value of x equals 5. The function x squared has not grown much, but the hyperbolic sign has a value approximately of 200. Therefore, this grows much more than the function x squared. My intention in this example was that you could see the similarity between its graphics, because it really appears in some problems. For example, to calculate the area enclosed between the hyperbolic cosine and other function. And in this case, I would need to know a little bit how is the representation to plan the problem well. I hope these problems serve as helpful in the future. See you soon.